Hello, it's me Vince, and welcome back to another IB Math Speedrun. So in this one, we're going to be going over chapter 7.1 still, and continuing on to the next part, which is about definite integrals. So let's jump right in. So what is a definite integral? Well, first we got to talk about what is one of the most important uses of the integral. Like for now, we've just been using it as a sort of antiderivative, but one of its most powerful uses is to find the area under a curve. So if we try and find the area, a good approximation might be to just draw some rectangles, take the lowest point on the curve, and then sum them all up. And this would be a good approximation, but it would not be exact. So we can increase the accuracy of this approximation by making the rectangles have smaller widths. So in this case, if we have something like this, this, that, this, if we have smaller widths, then we get an area that's closer to the actual area. And so if we have even smaller and smaller widths, in other words, if the widths tend to if we have more and more rectangles, where if we have the number tends to infinity, actually, this should be the limit as the number tends to infinity of I equals 1, the sum of each of the rectangles area, which we can find by saying the function at that point, times the change in x, then we can get an infinitely precise area. And so, yeah, it can be proven that the area under the curve is given by this function. And this is related to the integral of the function. The proof is, of course, you don't need to know it. So the definite integral, we've already talked about indefinite integrals, but a definite integral, which has starts at a and stops at b, is equal to the limit of infinity of this Riemann sum. We call this a Riemann sum. And so it gives the exact area of a curve between x equals a and x equals b, as long as f of x is continuous over that interval. So if we integrate a function with these two limits, with respect to this will give the area of the function under these two. And this is always gives a numerical answer. It's very important. So some properties of definite integrals is that, first of all, if we take an integral one way, it's equal to the negative of the, if we flip the coordinates around. If we take an integral at the same point, this is equal to 0. Like if the 2 points are exactly the same, of course the area will be 0. If we, again, like most of the indefinite integral properties carry over. So if we have a function being multiplied by a constant, then of a definite integral, this is equal to, if we can take out the constant from it, of f of x to dx. And the same goes for adding two functions together. And there's one last thing to note. It's if we have two bounds, a and c, of f of x, and we're adding it to two bounds of c and b. Notice the order. A is at the bottom, c is at the top, and then c goes to the bottom. If we take this function again, this will actually be equal to the integral between a and b of f of x. Yeah. And so there is a few other things to note about definite integrals. And first of all, when the function is negative, then if we simply integrate the function, definite integral, it will also give a negative value, which of course we can't have negative values for the area. So the actual area will be the absolute value of this for negative values. Actually, for all values. So the thing is, if we do have a part of the curve, say a part of the curve is positive and a part of the curve is negative, we need to use that rule where we can add two integrals together to split the integration of this into two. So first we integrate between these 2 points, and then we integrate between these 2 points, and then we flip this, we get the absolute value of both, and then add them together to get the true area. And finally, we get to the fundamental theorem of calculus, which is if f is continuous along a and b, and f is an antiderivative, then the integral of a and b of fx dx is equal to the antiderivative of b minus the antiderivative of a. So this is actually how we calculate a definite integral. We calculate the indefinite integral, and then we get the value for the upper bound, and we subtract the value of the lower bound from it. So that's a very important relationship to know. And so now we can jump into some questions. So yeah. So I'll be doing the odd ones. So first, integrate y is equal to 5 from x is equal to 0 to x is equal to 4. And this is a very easy integral. I mean, really, we're just getting the area of a rectangle with 4 and height 5. But if we integrate this, oh, and normally, of course, when we get the area, we're referring to the area bounded under the x-axis by the two side limits, the curve itself and the x-axis. So if we're getting 5 dx, this will be equal to 5x plus c. But you'll notice for definite integrals, we can ignore this plus c, and here's why. So we know that if we take 0 and 4 here, this will be equal to 5x plus c, where we substitute 4 in. So this will be equal to 5 times 4 plus c minus 5 times 0 minus c. Since if we're subtracting two antiderivatives, these constants of integration cancel out. We're simply left with this. So we can usually ignore this constant for definite integrals. So now we have 5 times 4 minus 0, so the area is equal to 20, like we might expect from a rectangle with height 5 and width 4. Hello, sorry about that. And let's move on to the next question, which is where we have to find the definite integral of x is between -3 and 3 of y is equal to 3 minus the absolute value of x. And so how do we integrate an absolute value function? Well, we actually have to split it into its piecewise components, because 3 minus absolute value of x is equal to 3, I guess, minus x for when x is greater or equal to 0, and 3 plus x for when x is less than or less than 0, I guess. So now we've done that, we can now integrate this function. So this will be equal to, if we integrate this top part, we get 3x minus 1/2 x squared, for x is greater or equal to 0, and 3x plus 1/2 x squared, for which x is less than or equal to 0. Less than 0. And so now we have to use the property where we can split limits apart in order to get this. So we have the limit from -3 to 0 of this function, say y, plus the limit of 0 to 3 of the same function should be equal to the total limit. So we can get these two. First, -3 and 0, well, we'll use this equation here. So when the antiderivative is 0, we have 0 effectively, minus, and when the antiderivative is -3, we have 3 times -3, -9, plus 1/2 times 9. So -9 plus 9 over 2. So this should be equal to minus 9 over 2. And so next, let's evaluate this for between 0 and 3, and we should get that this is equal to 9 over 2 minus 0. So we're adding 9 over 2 and 9 over 2, so we get the area underneath the curve is 9. And we can verify this because this graph should look like that. And so we can simply get the area of a cube with length 3, with side length 3. So this should be equal to 9. Next, we need to find the area bounded by the lines the lines y is equal to x plus 3, y is equal to 6 minus 2x, and the x-axis using appropriate definite integrals and geometry. So what would this look like on a graph? Let's try and sketch this out. So y is equal to x plus 3 would look like this. Y is equal to 6 minus 2x would look like that. So we're getting this area here, it seems. So what we can do is we can actually get the integral of x plus 3 until the lines intersect. So here, and then we can get the integral of 6 minus 2x after the lines intersect to the when x equals 0. Actually, bounded by the x-axis, so it should be here. So we need to, this should be equal to the integral of, well, when does x minus 3 touch 0? That's when it's negative 3. When do these two lines intersect? That is when 3x is equal to 3x equals 1. So we need to get the integral of negative 3 to 1 of x plus 3, plus the integral of 1 to 0 equals 6 minus 2x, 2x equals 1 to 3 of 6 minus 2x, it seems. So let's integrate this. We get, this is equal to the negative 3 and 1. This is what we used to notate once we've already integrated the function, and now we have to evaluate the limits of 1/2 x squared plus 3x plus with the 1 and 3 of 6x minus x squared. So this is equal to 1/2 x squared, so 1/2 plus 3 minus 9 over 2 plus 9, it seems. It's the absolute value of that plus, and now we have 6x and negative x squared, so we have 18 minus 9 minus 6 plus 1. So we can get here 1/2 minus 9/2 is negative 4. So we have 12 minus 4 is 8 plus 18 minus 9 minus 6 plus 1 is 9 minus 6, 3 plus 1, 4. So 8 plus 4, so the area should be equal to 12. And let's check if this is correct. We can simply use 1/2 base times height. So this is, we said this is negative 3 and this is 3. And the height will be when x equals 1, so the height will be 4. So this will be 4 times 6 over 2, which is indeed equal to 12. So we are correct. Okay, on to the next one. And the next one involves find the areas bounded by the function, x-axis, and the given lines. And the function is y is equal to x squared minus 5x minus 6 between x is equal to negative 1 and x is equal to 6. So the two roots, more or less. So we need to integrate between negative 1 and 6 of x squared minus 5x minus 6. So this is equal to negative 1 and 6 of 1/3 x cubed minus 5 over 2 x squared minus 6x. And we can eliminate plus c, so now we have 1/3 times x cubed, so that would be 36 times 2, 72, minus 5/2 x squared, so this is 5 over 2 times 36, 5 times 18 is 90, minus 6 times 6, so minus 36, minus 1. Oh, so yeah, this would all be below the x-axis. So minus 1, minus 1/3. No, that's plus 1/3 since we have minus 1 cubed. So it would be minus this entire thing. Minus 5 over 2 x squared, which is plus 5 over 2 since we have to subtract. And then minus 6 times minus 1 is 6, so then we have minus 6. So if we add all of this up, we get, let's add up all the integers first. 72 minus 90 minus 36 minus 6, so we get negative 60. And then 1/3 plus 5 halves. What's that? So we can, this is 3, this is 2, 15. So 60 plus 17 over 6. So this should be equal to negative 360 plus 17, and so negative 343 over 6, it looks like. So the area is of course positive, absolute value. So this should be equal to 343 over 6. Yeah. Next question, and the final question is, show that 4 sine x plus 3 plus x over 3 plus pi over 2 is equal to 0 when x over 3 is equal to n pi minus pi over 2, where n is an integer. By taking two appropriate values of n, find the first two positive x-intercepts and negative x-intercepts. Hence, find the total area bounded by the curve and the x-axis between x is equal to negative 3 over 2 pi and x is equal to 9 over 2 pi. Okay, so this doesn't look too hard. So 4 sine x over 3 plus pi over 2 is equal to 0 when x is an integer. So we need to prove that sine x over 3 plus pi over 2 is equal to 0 when this inside is integer, and that's not too hard. When x over 3 equals n pi minus 2, because this will equal 0 when itself equals 0, or it equals a multiple of 2 pi. So x over 3 plus pi over 2 is equal to n pi. So we have x over 3 is equal to n pi minus pi over 2. So we've proved that part successfully. And then we need to find the first two positive x-intercepts. So the x-intercept is when y equals 0. So this will be the first two positive x-intercepts. So we can simply substitute n equals, 1 and n equals 2. So for n equals 1, we have x over 3 is equal to pi over 2. So x is equal to, what is this, 2x? No, x is equal to 3 pi over 2. And the next one would be x over 3 is equal to 3 pi over 2. So x is equal to 9 pi over 2. And the two first negative intercepts should be x over 3 is equal to negative pi over 2. So x is equal to negative 3 pi over 2. And x is equal to negative pi. X is equal to negative 9 pi over 2. So these are the first two negative x-intercepts, and these are the first two positive x-intercepts. So hence, we need to find the area bounded by the curve and the x-axis between negative 3 over 2 pi and 9 over 2 pi. So, okay. So we need to integrate this. And we need to find the integral between negative 3 pi over 2 and 9 pi over 2 of 4 sine x over 3 minus pi over 2. And so, well, we know that this flips twice. So this flips once because there's one x-intercept between the two. So we need to find the integral between negative 3 pi over 2 and 3 pi over 2. Let's just integrate this first. You know what? of integrating this, we will get negative 12. Oh, is it frozen? Negative 12 cosine x over 3 minus pi over 2. And then plus, yeah, I believe that's correct, plus negative, 3 pi. The integral between 3 pi over 2. Actually, we can just double this since we know this is a sine function, so the integrals should have the exact same area, just in one in the positive and one in the negative. So we have 2 times that. So we have 2 times negative 12 cosine, what's negative pi over 2 minus pi over 2, negative pi, plus 12 cosine 0. So in effect, we just have 2 times 12, which is 24. So the area under this curve should equal 24. Sorry, not 24. This should be 48. Because cosine negative pi is negative 1. So this would be 12 plus 12, 24 times 2, which is 48. So yeah, that's the answer. So that was all for today's speedruns. I hope you enjoyed them, and I hope to see you in the next one.